All right, guys. Hello. Hope you are doing well. I'm going to get right to it, okay? Because I want to keep things short. Don't want to do like 30-minute videos of this, okay? Okay, so last time we finished up with giving you an example of a pretty simple food chain. This one going with the sunflower to the fox and everything. And I asked you a few questions about those, and you should be submitting those, and I'll be giving you the whether or not your answers are correct. Now we're going to be expanding on that and talking about some trends as we move through a food chain, specifically up our trophic levels. Trophic levels are your position in a food chain or food web. It's where you are getting your energy from and why that matters and why an ecologist might specify an organism as one trophic level as another is for some of the trends that we're going to look at today. Okay. So, looking here at this odd-shaped pyramid, we're going from producers up to primary consumers, this caterpillar, secondary consumers, the bird here, and then tertiary consumers, this hawk. It's basically a food chain, right? Going from bottom to top. One of the trends that happens as you go through a food chain, up trophic levels, is that energy is lost. And this is really important. So there's only so much energy available for any ecosystem, right? It's not infinite. Some people think that, where the sun could produce infinite amounts of energy and so on. The sun produces a lot of energy. Not all of it gets to the earth, of course, and then not all of it actually gets to a form that we can use, right? We can't take energy from the sun, right? We have to get our energy from the organisms we consume, and that energy that we're getting is a kind of a watered down version, so to speak. Why is that? So let's see here. Each trophic level, people have studied this extensively, loses roughly 90% of the energy from the one before it. So if we're going to say this flower producer has 100% of the available energy, however much energy that is. So as much energy as they can get, that's how much the ecosystem starts with. That's what you are allotted. Okay, so they get 100%. As you move up one trophic level to your primary consumers, these snails right here, they only have 10% of that original amount. It's only the original amount. Okay, so you're losing 90%. How are you losing that? You're losing that as heat, right? It's easy to think about that for us, right? We are warm organisms. We're hot, right? We keep our body temperature at about 98 degrees all the time. That's really hot, right? Most things in the world are not 98 degrees, right? We're very above the average temperature, no matter what temperature it is outside. So we have to eat a lot, we have to consume a lot to keep that body temperature up, right? Think of like a little mammal you see running around outside, or a hummingbird constantly moving, always moving, running around, constantly on the alert. They have to eat constantly to keep that up, right? Contrast that with like a reptile, which is mostly just sitting there doing nothing. They're conserving energy, but they're still losing energy as heat. Even plants lose energy as heat. Now, you don't really think about that because if you put your hands up against a tree, it's not like it's emitting heat. At least it's not in a large amount, but it is. So even all plants, all reptiles, every living thing loses energy to the environment as heat. Okay? And once that heat is in the environment, you can't get it back, right? If you're outside running, your body's really hot, right? You're releasing a lot of heat. You can't take that energy back into you. It's gone, right? So that snail has 10%. If something eats the snail, it would be a secondary consumer like this frog, and it only has 1% of the original amount. If the fox eats the frog, a tertiary consumer, the fox is, it would have 0.1%. If something were to eat the fox, it would have 0.01%. If something were to eat that thing, it would have 0.001%, and so on. This is why we only see usually about 4 to 5 trophic levels. You rarely see more than that in an ecosystem. Why? Because there's just not enough energy. If something were to eat this hawk, it would only be getting, let's see, what is that? 0.01% of the available energy in the ecosystem. And if something were to eat that thing, then it would get 0.001% and so on. So this is why we only see like Once you get to like tigers and bears and stuff like that, there's not like just an increasingly larger animal that eats the thing before it. It's not like we have a thing larger than a bear that eats the bear, and then a big monstrous animal that eats the thing that eats the bear, and then there's an even bigger creature the size of a house that eats the thing that eats the thing that eats the bear. It stops after a while. Why? Because there's just not enough energy. So it's capped at a certain point. So that's why we usually only see about 4 to 5 trophic levels in an ecosystem. And if you think about this, right, this is tightly connected to another trend called biomass. Bio means life, mass means the weight of something, so it's the weight of life. Specifically, it's not how big a thing is, right? Like an African elephant does not specifically have a high biomass because it's not the weight of one single organism. Biomass is the total weight of that entire population. Or maybe you'd be interested in the whole species on the planet. So those are two separate things. Okay, just because you're a big animal doesn't necessarily mean you have high biomass. So it's the total mass of the species. And we base this off of estimates of populations, right? We can't get an exact number, right? People heavily study biomass of people because we're very curious as to how many people could really live on the planet, how much energy are we consuming, how much space do we take up, and how much do we need, and how many people could this planet really support. We monitor that quite a lot. The trend is that biomass generally goes down as you move up a food chain. Okay, so if we go back to our simple food chain here, biomass would also go down. You would have more flowers, less snails, less than that of frogs, and less than that of foxes. Why is that? Well, it's because the energy is going down. If you have less energy, you have less calories to support the literal organic tissue of a thing, right? So if there's not enough food to go around, it can't be supported. And if you think about this, I mean, if you just look outside, how many plants do you see? A lot, right? I look outside and I see it's just green, right? There's grass covering the entire ground. There's flowers. I see like 30 trees outside my window right now. There's tons of plants. They're everywhere, right? How many herbivores do you see? Well, a decent amount. I usually see a few rabbits every day, some squirrels, some chipmunks, and a lot of insects, things like that, right? Decent amount. How many things that eat those do you see? Well, decent amount, sure, but less. And then how many like hawks do you see? How many coyotes do you see? How many of those top tier predators do you see? Not very many, right? It's not like there's 10,000 hawks flying around in my neighborhood, right? There's only a couple that fly around here because there's not enough energy. So their biomass is actually quite low, even though the hawk is technically the biggest organism on this list. Their biomass is the smallest, and the biomass of the plants would be absolutely enormous. Okay. Here's some examples. Look at these. Humans, earthworms, blue whales, termites, and bacteria. Worldwide, what do you think would have the least, the most, and so on? Here are the answers. Humans have about 350 million tons. If you just weighed us all on a big giant scale and put all people there, we'd have a couple 100 million tons. Earthworms, 5,000 million tons. Again, earthworms are far smaller than people, but they're lower on the food chain and they have more available energy. There's much more of them. Blue whales. Blue whales are the biggest animals in the whole world, and yet they only have a few dozen million tons. So your size doesn't necessarily mean you have a large biomass. In fact, it often means it's a smaller one. Termites, low on the food chain. They are primary consumers. They've got about 445 million tons worldwide. It's a lot, right? More than people. Bacteria, crazy amount, 450,000 million tons. That's 4.5 billion tons. That's a lot, right? So those are the two trends. Biomass goes down and energy availability goes down as you move through a food web or food chain, and those two things are tightly connected. Okay. Last thing, Rarely would an ecologist specifically look at a food chain. If you're really interested in what's happening to a single calorie as it moves through an ecosystem, sure, you might do that. But a food web shows the more complicated relationships in an ecosystem with its community. Um, so, just like a food chain is like a chain, a link of organisms, a food web is a big conglomerate mess of interactions because it's complicated out there, right? So interconnected food chains in an ecological community. Here's an example. So these are just a bunch of food chains, right? This one's a little bit more complicated. Our producers are these phytoplankton down here, these algae. Those are our producers, right? So they're at the bottom of the food chain. They're the producers. These krill are eating them, so they'd be a primary consumer. These krill are eaten by leopard seals, Weddell seals. They're eaten by these other penguins. They're eaten by fish. They're eaten by the albatross. They're eaten by the octopus. They're eaten by crustaceans. They're eaten by a lot of things, right? These whales. Um, and then let's see, we can look at like this emperor penguin can eat the squid. The emperor penguin get eaten by the leopard seal. You can follow anything here. And these are important because we can see what would happen in the ecosystem as populations go up or go down. For example, we've been seeing big changes in whale populations around the world due to hunting and climate change and things like that, and their populations have been going down. What happens because of that? Well, look at all the things that they eat. That's going to cause those populations to increase, which could maybe increase the populations of the other things that eat them. But then as those other things increase, the original thing would decrease, and it becomes this very complicated relationship. So we might want to monitor a species and what's happening to it, and maybe predict what would happen to the ecosystem if their populations would go up, go down, or maybe if they went extinct. So this one's a little bit more complicated. Here's a simpler one, right? You've got your producers down here at the bottom, primary consumers, secondary, tertiaries. It's roughly leveled. And notice how, like, the frog has many arrows going to it. It eats many different things, and also it has multiple arrows that it's going to, meaning it gets eaten by multiple things. So notice also the frog is occupying more than one trophic level. So I'm going to be having you guys make your own food web. Don't use this one. Don't use this one. Don't just look one up. I want you to make your own, right? Don't just have one arrow pointing to each thing. In reality, each organism will be eaten by and will eat multiple things, usually, except for things like a panda that eats basically only bamboo, right? But they'll usually eat all kinds of things, okay? So there's a pretty good example for you what a food web would look like, okay? Here, not to give you a headache, this is one that someone produced by people like doctorate students making a food web that was as accurate as they could possibly make it. It's pretty impossible to read, right? You can see like these amphipods down here where my cursor is. They've got like, I don't know, 15 arrows, 20 arrows going from them and the one going to them, and then it gets lost in this big mess here in the middle. These people went out to actually make a food web that shows every single interaction of every single species in that community, and it gets pretty complicated. So even the food webs that we make in simple terms, those are not perfect, but they're better than nothing to predict what happens in an ecosystem. Okay, so you'll be making your own food web, not like this, more like this, and there's some questions that go along with it, everything. I'm not going to explain it all here. It's in the directions. Okay, all right. I think that's it, okay? This is going to be your only assignment for this week. It's a bigger one. I expect you to be emailing me questions throughout the week, making sure that you're done correctly. Read those directions carefully, okay? Alrighty, I'm going to stop recording. See you guys.